So in this video, we're talking about sequences and sums. And this is a very cool topic because we're looking at patterns in mathematics. And this has a lot of applications in many kind of weird ways. But what is a sequence? So it's a list or a set of numbers that make up a function typically. And they can be finite, meaning they end, or they can be infinite, they continue on indefinitely. Classic example of a sequence is the Fibonacci sequence, which I have here written to the first 5 terms. If you don't know the pattern to the Fibonacci sequence, I encourage you to pause the video and look at it. But here's the pattern. We're going to take the first 2 terms, add them together, and get the next term. So 1 plus 1 is 2. Then we're going to add the next 2 terms to get the next one. So 1 plus 2 is 3. Then we add the next 2 terms, add them together, and get the next one. 2 plus 3 is 5. Using this same process, what's the 6th term? Well, the 2 previous is going to be 4 and 5. So it's going to be 3 and 5, which gives us 8. And the pattern goes on indefinitely. Now, this is a list, as I've written it out here. You can also write a list like this: 1, 1, 2, 3, 5, 8, and continues on. This is the first way to write a sequence. There's other ways to write it. And the next way is called the nth term, which is more like a function that you're used to. So here's an example. an equals 4n minus 1. This is an nth term using this sequence 4n minus 1. And the nice thing about this is that you can find any term you want. So let's find the first 5 terms of this sequence. So a1, what we're going to do here is we're going to take the 1, we're going to plug it into the n. Just like in a function where you input x, a number in for x, that means every occurrence of n is going to be changed to 1. And that's how we actually find the value. 4 times 1 is 4, minus 1 is 3. A sub 2, same process. 4 times 2 now, because that's what n is, minus 1, that's 8 minus 1, so it gives you 7. A3 is 4 times 3 minus 1. 12 minus 1 is 11. A4 gives us 15. And A5 will give us 19. And so now we can rewrite this as a list. So this is the same thing as the list of 3, 7, 11, 15, 19, and it can go on indefinitely. Now what's the pattern? The pattern is that we start at 3 and then we add 4. We start and add 4. We go from here, add 4 to the next one. And that's the pattern there. It's so in this case, we start with 3 and we just take every 4th number from that point. Okay, so that's the second way we can write sequences. The last way is kind of the most interesting. It has a number of applications on its own, and it's called recursive. So the recursive sequence is one that uses the previous terms in the sequence to define the next one. In fact, the Fibonacci sequence was used, can be written recursively, and it's very easy to write recursively. This is the Fibonacci sequence. For the nth term here, this is the nth term. We look at the 2 previous terms. So n minus 1 is the 1 previous, and n minus 2 is the 2nd previous term. All right? And the only way you can have a recursive sequence is if you have a starting point, because obviously, where do we start with this information? And so that's always going to be given. If it's not given, then you can't do anything with it. But for the Fibonacci, we can write these as our starting points. We need 2 here because this one uses 2 previous terms. But we have to, so we can go on and we can find any term. The one downside about recursive is that you cannot find any term you want. You have to start at the beginning and build your way up to like, for instance, the 53rd term. We can't find the 53rd term right off the bat. We have to work our way there. Let's look at a different recursive sequence and see how it works. So here I have this recursive sequence given, where it's pretty much we take 5 times the previous sequence. We also have given to us that a1 equals 2, and that this is only for n greater than 1. Normally we only allow n to be greater than 1. Sometimes we allow n to be 0. That's a topic for another time. So if a1 equals 2, then what does a2 equal? Well, it equals 5 times a2 minus 1, which is 5 times a1. And we know what a1 is, right? a1 is just 2, so that gets plugged in. 5 times 2, which gives us 10. Okay, so a3 is 5 times a3 minus 1, which is 5 times a2. And we know what a2 is, we just found it. So we're going to take what we just found. I should write it like this. Plug it into here. Gives us 5 times 10, which is 50. So a4, using the exact same reasoning, is going to be 5 times 50, because it's just the previous term, which is 250. And finally, a5 is 5 times 250, which was going to be 1250. And this, of course, can go on indefinitely. That's the recursive formula. This one just uses 1 previous, so we only needed 1 starting term that was given to us. Like I said, the Fibonacci required 2 because we had 2 terms given that were needed to find the next one. Okay. Sequences are found in many places. Probably the most notably is in algorithms for computers. And typically when we have algorithms, these recursive definitions tend to be less costly for different programming languages. Sometimes they aren't, but they tend to be less costly for memory, which in turn, saves money. That's the reason why we have different versions of writing a sequence. Okay. One of the most, a sequence that's used very frequently in mathematics is the factorial sequence. And this can be given in a number of ways. We typically don't write it recursively because it's not really useful, but you can write it recursively. And this is what the sequence looks like normally. This is the nth term, which is just n times n minus 1 times n minus 2, all the way on down. We're going to multiply all the way on down to 1. And that's where we stop, is when we multiply by 1. This exclamation mark, that's what is given as like a shorthand notation in mathematics, because this is used pretty commonly. So the exclamation mark means take the factorial of the number that's in front of it. Okay, so we can write this recursively. Like I said, it's not terribly useful because we want to actually use it in mathematics, but in computer programming, that can help. In this case, we have to have a starting term, and you can say a1 equals 1 for that. So to give an idea, what's the first 5 terms of this? Well, a1, we can follow this thing, but typically a1 is just given as 1. As you can see with this recursive sequence, it's given there. You can give it in the previous one, but 1 factorial is just going to end up being 1. I guess I can write that here. A2 is when it gets a little bit more interesting. and that is 2 factorial, which is going to be 2 times 1, which is 2. A 3 is 3 factorial, which is 3 times 2 times 1, which equals 6. So now we kind of see the pattern a little bit more. A 4 factorial, 4 times 3 times 2 times 1, which is 24. And finally, a 5 factorial, 5 times 4 times 3 times 2 times 1, which gives us 120. Now, there is a pattern here that's separate from, just the obvious 1, then 2 times 1, then 3 times 3 times 1, and so on. Is that as we go from the previous to the next, what we do is we multiply by the next term, by the next in term that we're doing. So we're going to the third one here, so we're going to multiply by 3. We go on to the fourth one here, so we multiply by 4. Go on to the next one here, and we multiply by 5. You see that there's this interesting pattern for this factorial sequence. Okay, let's use this in a problem just to kind of simplify things down. We're going to look at this problem here. And there is reasons why I'm looking at this problem. This is actually a combination, which we won't talk about in this video, but combinations use factorials frequently because they're talking about counting a certain number of combinations of like if you choose 2 people in a line of 6, how many possible choices can you make that are distinct? So that's where this setup comes from. But to actually solve this, what we do is we just open up the factorial, or expand it, I should say. 11, 10, 9, 8, 6, 5, 4, 3, 2, 1. Now, normally we don't have to actually write this thing all the way out. A lot of times we can do some simplifications before writing it out, but I just want to write it out to show you what I'm doing. So this is 2 factorial is 2 times 1, or multiplying, that's what this dot here is, by 14 factorial. So let me just expand that all the way out. Again, we're just multiplying everything. Whoops, I wrote 8 twice. 6, 5, 4, 3, 2, and 1. Okay, and now we can do the simplification, and hopefully you can see that all we're doing is multiplying here, so we can remove common factors, and there's a very long common factor here that we can cancel. Okay, now we can also cancel a 2 in the bottom and the 2 that's in 16 on the top. So this now becomes 8 times 15 over 1 times 1. Well, that's just going to be 8 times 15, which is the same thing as 4 times 30, so 120. So factorials, typically, they're used in pairs like this, but depending on the situation you're looking at, you know how to expand a factorial and cancel common factors, things like that. Okay, sometimes we want to find the sum of the terms in a sequence. Now, this is technically called a series. You take each term and you add them together. And there's a lot of different mathematical applications for this. They're more complex than what we're currently looking at. But the series are very powerful tools to define functions. So let's look at just a beginning understanding of what a series is. Typically, when we do series, we have to have an index term, and that's normally I. I just runs through a certain set of numbers, like 1 through 10 or 1 through 20. But you can also use J or K depending on your situation. These are typically the 3 that are used the most. You could use any number or sorry, any letter, but we're going to be looking at these three specifically. So I can write a sum as this. The sum from I equal to 1 up to 4 of the sequence I plus 2, I plus 3. So we have a couple things here to understand. We have this inside part. This is what's actually being summed up. This is the sequence, okay? Then we have the indices. It's going from 1 up to 4, meaning 1, 2, 3, 4, okay? That's what I is going to be taking through. And finally, we have this summation symbol here. I think it's capital epsilon in the Greek. And this means that we're going to be summing up each of the terms, okay? It's kind of the functional notation here. Okay, let me clean this up so it's a little bit clearer what we're looking at. So to actually do this, it's quite simple. We take the first I number, in this case, I equal to 1, and we plug it into our function. So we have 1 plus 2, 1 plus 3. Okay? And that's the end of the first term. And so when we come to the end of the first term, we put a sum, because the symbol here, this backwards E, is the summation. So you're going to put a plus there between each term. Then we're going to add 1 to I. So now I becomes 2 because it was 1, so now it becomes 2. And then we go I equal to 2, and we're going to plug that into each one of these terms. That gives us 2 plus 2 and 2 plus 3. And then we add the next term, which is going to be I equal to 3, which is going to be 3 plus 2 and 3 plus 3. And finally, we add another one to I, so I becomes 4. And 4 is the stopping point here. So that's going to be the last term in our series. 4 plus 2 and 4 plus 3. Now we just expand each of the terms and add them up. So 1 plus 2 is 3. 1 plus 3 is 4. 2 plus 2 is 4. 2 plus 3 is 5. 3 plus 2 is 5. 3 plus 3 is 6. And we get 6 and 7. So you can see what we're doing here is we're adding up all the concurrent pairs and also, continuing on towards, higher and higher numbers. All right, 3 times 4 is 12. 4 times 5 is 20. 5 times 6 is 30. And 6 times 7 is 42. Adding that up gives us 102, it looks like. Nope, 104. 104. And so that's the summation or the series for this sequence, just going from 1 to 4. This is called a partial sum because this sequence could go on indefinitely, but we're only summing up a portion of it, or a partial sequence of it, 1 to 4. Okay? Now, we're going to be looking at another one here. The sum from k equal to 1 up to 5 of I plus 2. Let me rewrite this a little bit better. I plus 2 factorial over I factorial. And we're not using i's, we're using k's actually. So let me change the indices here to conform. So we have the same index. Okay. You can see that I wrote the summation just slightly different. I wrote the I equal to 1 and 4. I wrote these just in front, so I just moved them forward some. So I could write the 5 on top and the k on top. It doesn't matter. What's important is that if the k is on bottom, or the k is on bottom, so that tells you where it starts, and the number on top tells you where it ends. So we're going to run from k equal to 1 up to 5. Okay? All right. Adjust this slightly. All right, k equal to 1. Plug in 1 to where k is, so we get 1 plus 2 factorial over 1 factorial. And that ends the first term, so we're going to add, and then the next index is k equal to 2. So 2 plus 2 factorial over 2 factorial. 3 plus 2 factorial over 3 factorial. 4 plus 2. And the last one, because k equal to 5 is the top portion, so that means we're going to end here, is that. Now this gives us 3 factorial over 1 factorial, 4 over 2, 5 over 3, 6 over 4, and 7 over 5. And you can see the pattern there, right? We're increasing by 1 on the top and the bottom, and of course the bottom is shifted down to 2 units less than the top. Okay. Now, I'm going to only expand the first 2 terms because I want to show you the kind of thinking you can do so you don't have to expand every single factorial. That would take a long time. So on top we have 3 times 2 times 1, and on bottom we have 1, because 1 factorial is 1. And though 1 doesn't really do anything, we can think about canceling the 1s, and we're left with 3 times 2. Okay? The next term is 4 times 3 times 2 times 1. And on bottom we have 2 factorial, or 2 times 1. And those will cancel with the 2 times 1 on top and leave us with 4 times 3. Okay, this same reasoning we can do for the rest of them, because 5 factorial, right? 5 factorial does have 3 times 2 times 1. This portion here is just 3 factorial, and those will always cancel. So really, this next one is just going to be 5 times 4. And 6 factorial over 4 factorial is going to be 6 times 5. And the last one's going to be 7 times 6. Okay, 3 times 2 is 6, 4 times 3 is 12, 5 times 4 is 20, 6 times 5 is 30, and 7 times 6 is 42. And we can expand this, add these up. Let me use a calculator here real quick. It actually is quite simpler than that, because if you notice that this is actually the same thing we had previously. Now that I think about it, we have 12 plus 20 plus 30 plus 42, which is 104. And then we just add 6. So we have 110. So what's interesting is that we actually got the same sequence from 2 different, I guess, ideas of what these sums are. Let me clean this up a little bit. It's easier to see. So I plus 2 times I plus 3 is almost the same as k plus 2 factorial over k factorial. And these kind of properties, if you're willing to expand this algebraically, you can actually find these properties out. It takes a little bit of work. The algebra is kind of tedious, but you can see those. All right, last part of this video is going to go from, we're going to go from this kind of portion, we're going to go backwards. We're going to go to the summation. So we're going to kind of like condense a sequence down to a summation. All right, let's look at this sum. And here, I'm not going to write out every single term because it would take too long, but here we go from 1 to the 4th all the way up to 12 to the 4th. And we are in fact summing each one. So we know we can use the summation notation for that. And now the question is, where do we start? So I'm just going to give this the index of I. And it looks like we start with 1 because 1 goes to 2 to 3 and then goes on up all the way up to 12. So I can say it starts at 1 and it goes up to 12. Now what goes on the inside here? Well, what's happening to the 1? The 1 is being put to the 4th power. The 2 is being put to the 4th power. The 3 and all the way up to the 12. So we can think about it saying I to the 4th power. And I think that's a very good starting point. Now, I would always check. For me personally, it's easy to get these things kind of slightly confused and you make it a simple error. So actually go through, use this definition that you just created and expand it and see if in fact you get what you started with, this original sequence that we had here, or I should say series. So when we plug I into here, right, I equal to 1 is plugged into there, we get 1 to the 4th power. Okay, and then we increase our index, so I equal to 2, and goes 2 to the 4th power, and then 3, and then all the way on up to where we end, which is 12 to the 4th power. And you see that we do in fact get the exact same thing. So we know that our sequence, or sorry, our series is correct, and it's the correct condensed form of it. All right, let's look at one that's a little bit different. 1 over 3 plus 2 over 4 plus 3 over 5 plus all the way on up to 16 over 18. Now, we want to have a starting index, and we always like to start with 1. So let's just use j here, j equal to 1. That's what we want to start with. So can you find the 1 that's in this original starting value here, the first one in the series? The 1 is here on top. And we can see that 1 goes to 2, 2 goes to 3, and then it's going to go to 4, 5, 6, 7, 8, all the way on up to 16. So our starting value is 1, and our ending value is 16. So we know where our j is. The j is going to be on top of the fraction. Okay? Now, what happens to the bottom? Well, we start with 3, and then we just add 1 to 4, then we add 1 to 5, and then we keep going through all the way up to 18. And you may also notice that, so this is increasing by 1 each time, all the way on up to the last one. And you may also notice that 3 is 2 greater, or I should say, I should go the other way. 3 is 2 greater than 1, okay? And then 2 is 2 greater, sorry, 4 is 2 greater than 2. 5 is 2 greater than 3. And you have this constant between each of these terms. We have this additional 2. So we know that j is going to be involved because we're increasing by 1 each time. And we know exactly how j is involved because it's 2 more than the top. So really, it's just going to be j plus 2. The top number plus 2. And the top number increases each time, which means the bottom will increase each time. Now, there's no way to know for sure that this is correct without testing it, okay? I always recommend you test your series to make sure it's correct. All right, let's plug in 1 into the bottom, or let's plug in j equal to 1 into our sequence here. Get 1 plus 2, and plus. J becomes 2 now. J is 3 now. Then I'm going to just draw dots and go to the last one when J is 16. We get 16 over 16 plus 2. Now let's simplify this. We get 1 over 3 plus 2 over 4 plus 3 over 5 plus all the way on up to 16 over 18. And those are in fact the exact same series, which means our condensed form is correct.